Hey, it's time. Welcome back, everyone. We're almost done with week 3, which is kind of amazing. When week 4 is done, that's the 25% mark. So we're almost a quarter of the way through the entire semester. Congratulations. We're nearly done with chapter 3 as well. We have one more big section after 3.5. We're going to skip to section 3.7. And these will probably take about a day and a half to get through on that section there. But after that, that's going to be the material we'll see on our very first exam. So it's going to involve sections 3.1 through sections 3.7, skipping section 3.6 right there in the middle. And it's going to be scheduled for, we put in a revision here, Tuesday, September 19th. So we still have some time before we are really into it on that exam. I'll be discussing it quite a bit more on the next week here between September 11th, September 17th. But any questions at all so far, folks, before we get going? Okay, maybe another thing I should mention about the exam is if you did want to start early studying, I have some sample exam problems that are posted here as a PDF. There's also answers at the very back. Or hang on, let me recall. I do these a little bit different depending on the class. This is just a set of problems from the actual text. And I only selected the odd problems so that the answers are on the back of the book. But we'll talk about those more as we get closer to the exam. Also, for the exam itself, keep in mind, there's 2 calculators that are allowed for the exam, the TI-30XA or the TI-30X2S. The reason they make that requirement is they have the math department requires it to be closed graphing calculators for this one course. And so those are 2 typical scientific calculators that do really well. If you have another calculator that you're just comfortable with, it's not a graphing calculator, it's not a cell phone, and you would like to use on the exam, just take a picture of it, show it to me so I can see the model number, and I'll let you know if it's something the math department would be okay with or not. So if there's other calculators you like to use, I'm not going to make you change if they fit this general type of calculator. Well, other questions at the moment, folks, so far? Okay, with where we're at right now, we're going to take a look at the transformation of functions. This section is a little bit tricky, so it's a good one to take a look at first in the book I mentioned. And so is the next section, 3.7. We'll take a little bit more time on getting through these. And the brand new quiz is now posted. So we take a look at this. I posted it the other day and I already forgot what problem I assigned. That's kind of wild. That's one of these kinds of problems. So same kind of thing we did in section 3.4. I'll give you 2 functions, form their difference, get an expression out. Multiply the functions, evaluate at -2. So this one should come out as a number. And this one's a function composition. So if you go through the work we did in 3.4, you can take a look at some really close examples to this process here. So that'll be our 3rd quiz. I got the numbering right this time. Sorry for the typo on the other set. And this will be due next Tuesday, September 12th. Well, any other questions so far, folks, about the quiz or otherwise? Okay, let's close this and get back to where we're at. So we're in section 3.5, transformations of functions. Oh dear, I forgot one more announcement. Sorry about that. There's one thing I want to point out in ALEKS. I did have a question about this. In ALEKS, we always do our initial knowledge check, and that thing is long. It can take anywhere between, I'd say, 50 to 60 minutes on average for folks to get through. And when you keep on working on ALEKS, this pops up. And it's kind of like the worst thing you would ever want to see in ALEKS, right? It's another knowledge check. I've been working in the system, and after I finished section 3.4 this morning, I got this right here. And let me tell you the idea behind these. They're not like the initial knowledge check. They're a lot shorter. And the idea behind it is it's ALEKS' way of trying to get you to review the topics that you've learned in the past as you go through the course. So think of it as just an opportunity to review right in the middle. If you wanted to, it says, take your knowledge check now. They're really assertive about that. There's like a 23-hour window. There's no credit that's actually really tied to this. This is strictly review. You're always going to get credits by completing sections by the due dates. And so one little strategy that you can use is just skip that, go down below and go to section 3.3 and just click on there. You'll start working those topics. So you can keep on delaying the knowledge check for as long as you like. Depending on how the due dates fall, it might just go away, or it might be the only thing that's left to do, and we'll eventually have to do it. But I encourage you, if you're not really keen on reviewing right that moment, just skip to the actual section that you're working on, and that's never going to cause you trouble. Does that make sense to folks with those knowledge check issues? Okay, let me go back here, back to home. There's other things that you could do as well. Way down here is review for the knowledge check. For our class, that's really less helpful. The knowledge check for us is the actual review. For different ways people set up ALEKS, people sometimes lost points on these knowledge checks. That's not happening in this class, and that means the review is kind of irrelevant for us. So I would just say ignore that entirely. Well, I think that's my major announcements I want to make on ALEKS, but maybe just one more reminder. The due dates are only for pacing. If you miss in a section, maybe it's 3.3 or something like that. It doesn't mean you just lost points for that entire section. You'll just have to get an extension. You can go and click on the menu bar here, click on your grade book right here. I don't know what my grade is in the class. So far I have a 65% because of that section right there. It's only based off sections that have gone past the due date, giving a score on them. And so if I look at, say, this one, I didn't do too well, I would just send myself an email saying, hey, could you request and give me an extension on section 3.3? Any kind of email like that is always going to work just fine, and I'll always be happy to do that. Also, just a reminder, when we get to the end of this week right here, what I'm going to do in ALEKS is essentially just open up and extend all of the sections that are the exam, so that while you're studying for the exam, you can go to any section at all. So again, think of the due dates as pacing entirely, and you can always go back to those sections to increase your score. Okay, that's 6 minutes of announcements. That was a lot today. Any questions, folks, about any of those comments? Yeah, go ahead.
So with the exam being Tuesday, not next week, but the following week, is Tuesday class is going to be covering all of 3.7, and then we'll have a review day on Thursday, or how does that usually work?
We don't have reviews in this class schedule, but pretty much what will happen is we'll be finishing off section 3.7 on the Thursday of that week right there.
Okay.
If we finish early, we'll pretty much just open class up to any questions at all. So there could be like an impromptu review right in the middle. Other questions about that so far? Okay. And also, I'm glad you mentioned that. One of the reasons I like to post this really early is if you do start taking a look at these problems and start studying them over, say, around this week, you can bring them to class. I'll be happy to discuss those problems at the start of class as well. So really, that's a standard offer for any class. If you saw something that was just really, really gnarly in ALEKS and you want to discuss it, maybe take a screenshot, send it to me, and we can start off class just looking at that one problem. Other questions so far, folks, at the moment? Okay, well, let's jump back in then to section 3.5, the penultimate section for this list here on exam number 1. It starts off, well, with just a bunch of math out of nowhere. The reason I put in this graphic is this is what our book likes to call a set of toolkit functions. I just felt like these graphics were a little bit prettier than what our book did. Our book's free, so we can't blame them. And so these are the very common functions that we're going to see as we work through our chapter 3 and the rest of the semester. In fact, we've been dealing with a lot of these. We've been dealing with x squared. We've been dealing with, let's see here, square root functions like the semicircle function or an ordinary square root function. And we'll start studying each one of these in a little bit more earnest. If we take, say, this one, y equals x squared. Let's focus on that thing. And let's suppose we were to not do that. Plot it. Y equals x squared. So that's the graph they provided us. You could call it a y equals. Here in Desmos, you can also call it f of x equals if you like. And this Desmos, for us, it's just a graphic calculator that I like to use in class because it's easy to pull up. So you don't have to use Desmos if you don't like to. It's only an optional software. So there's x squared. There it is again right up here. But this section is about transformations of functions. So what we mean by that is if we want to move this function around, transform it, we might do something like, say, go a -3. What that has done is taking this function that had its lowest point right at the origin, that's its absolute minimum, and it's dropped it down to this location at -3. So we've transformed the function, we just moved it around is what we say here. We can do other wild transformations. We can go inside x and go x plus 1. And notice what that did. That is really weird, and it always kind of hurts my mind a little bit. When I put the -3, I expected the parabola graph to go down 3. It should, right? When you go +1, it goes to the left by 1, not to the right, which is really, really bizarre on this. So that's something we'll pay a lot of attention to. And it's a little bit easier once we actually write out these plots, sketch them out by hand. So see just how that works. Let's put another number inside or right in front of here. I'm going to put, say, just negative sign right there. If I put a negative sign, any volunteers for what would happen to this graph? Exactly, we're going to flip the whole entire thing. And that's what it looks like. I mean, I have to zoom out now. This extra negative sign has caused a reflection at the same time. And there's loads of other weird, wild things that we can do to this graph that we're going to get into today. What any questions or comments so far, folks? Okay, so the idea for us in this section, one of the reasons we'll take a little bit longer in these last two sections, 3.5, 3.7, is we want to practice working with each of these functions. I would say the semicircular function is kind of the odd one out, in all honesty. We may not use it a lot, but it's here. That's its formula right there. The other 5 we're going to be using quite a lot today. Any questions at all then before we go to our next set? Okay, so these are the basic functions we'll be working with. And we're essentially just going to move them around, compress them, stretch them, reflect them, and so on. The rules for all of that is this table right here. It's kind of a formidable table when you see what 1, 2, 3, 4, 5, 6, 7, 8 different formulas all at once. What the new equation might be for the function or the new equation for the point. But the more you work with this, the more it just becomes familiar. So our goal today is work with this a lot and see which of these different properties we'll be using on each one of the problems. For that end, I'm going to open up this document, again as a PDF, and I'll just take screenshots of this table each time we use one of these so we can see how it's used and what all this other information is saying on the table. So let's get started, folks. Here's our bona fide example 1. Our goal is to graph 2 functions, just an ordinary f of x equals square root x. Our book likes to call it, again, the toolkit function. It's like the basic square root function. That's why they call it that. And this one, g of x, that's our transformation of the function. Before we sketch it, it's always a good idea to look before you leap for this kind of process. So when you look at, say, that +5 here, anyone see what's going to happen to the graph? Should it go up or down? Exactly, this is going to send it up. And that +5 right here is what's happening in property 1 for these transformations. We have an addition of some constant, and every point on the graph is going to have +c added to it on its second coordinate. That's what's going to be moving it upwards by that amount, 5 this case. So here, I would just say go up 5. And that's the major idea with deciding where this function is going to end up. Next thing to look at is the -4. Now, if we have something right next to x, then we're dealing with something like this right here. We'd have let's see, a negative quantity, -4. So if c is a positive constant, then what's going to happen here is we're going to shift, again, it's really weird, to the right by c units, whenever we have that feature there. So because of the negative sign down in the function, I always want to move it to the left, but this one goes to the right. That really deserves an explanation for sure, right? But we'll see it as we actually start to graph this thing. So I'll say here, right 5. So the 2 properties we used on this one. Oh, thanks for catching that. Right 4 on that one. Oh, let me go to, there we go, right 4. Scroll down for just a bit. So the 2 properties we had to use was just property 1, property 3 for this particular problem. Now let's sketch the graphs and just see what they look like and see if they are really doing what we're expecting they should do. I'll use green for the original function and blue for the transformed one. So here's our big graph. I'll put both on the same set of axes. And like I mentioned before, At the very top of these notes, also throughout your book, they give you a huge list of toolkit functions. It is kind of overwhelming when you look at all those functions, but really the most important technique here is knowing what the domain is and just using the point plotting method. So if I have a square root function like this, it means the smallest number you could put in there is 0 because the domain goes from 0 with a bracket off to infinity. So I start by going like this. X and f of x equals root x. So there's my table. Pick the minimum domain element, which is 0 for this one. Let's just put in a couple easier to find points. 1 is not too bad. Let's maybe start evaluating them. We're putting 0 inside the square root right here. So this becomes root 0 equals 0. Of the second row, we're putting 1 inside the root function. So it becomes root 1. Square root of 1 is just 1. And now here's where it gets a little bit awkward. I could put in a 2, but the square root of 2 is just not convenient to plot. More nice to put in, say, 4, right? It's a perfect square. The root of 4 would give us a 2 instead. So no reason to work too hard. Try to always look for the easiest way to get out of this and get nice, fast to produce points. This produces a root 4, which gives us a 2, like we said. So here's our table. Think of this as the x coordinate. This is the y coordinate. First point is right here at 0, 0. Going down the row, we have a point at 1, 1. And then finally, we have a point at 4, 2. So here's 2, 3, 4, and a height of 2. Last thing to do is connect the dots. But note, it's absolutely not a straight line. It has some curvature to it. And so this graph looks about like this. I'll put an arrowhead here to just say it's going to the right forever. So we've got it, folks. That's our square root function. Any questions on producing this plot here? Okay, now for folks who are really good at this, and there's probably some of us in class today, if you know you're just going right 4 and up 5, you can sketch this extremely fast. Just take any point, move it right 4, up 5, and you're done. Plot the rest right after. Actually, I'm seeing I have a bit of a conflict here. Let me move these out of the way so it doesn't get too busy. That says right 5. Oh, I keep on doing that. Thanks again for saving me on that one. Right 4. I guess I just like the number 5. And this is up 5. Okay, yeah, go ahead.
I did have a question. So with the additional function and the transform function, are they both supposed to be plotted on the same graph?
For this problem, yeah, that was the intention. And when it comes to, say, like maybe a real exam problem, I'd probably have to be much more descriptive here. I would in fact plot a scratch paper here for you and say something like use the same set of axes. Other questions so far? Okay, so now let's go to the one in blue. And again, it's the same kind of strategy. You could either move the green curve up 4, right 5, or if you're new to this and you're just practicing, I encourage you to try this out again. No harm done. We're going to put in an x. We're going to put in a function. G of x equals root x minus 4. Got the 4 this time, plus 5. Now this time, we don't want to pick 0 necessarily. I mean, you can't. If you try to put in a 0, then here's what's going to happen. I'm going to delete this in a moment. Put in 0, that means you're going to put a 0 right here. That becomes root negative 4 plus 5. But that's now not a real number any longer. That's a complex value number. So we didn't actually have a value inside the domain when we picked x equals 0. So that's already a little bit weird. When we go here, the domain is actually found by setting x minus 4 greater than or equal to 0, which would mean x is greater than or equal to 4. We had to convert that to interval notation if it was, say, like an official problem finding the domain. But remembering domains and ranges tells us the smallest value you can put in here is actually a 4. And really, we really ought to. Let's throw in a 4 right here. Then the output will be root 4 minus 4 plus 5. That's just the square root of 0, so it's 0 plus 5, giving us a 5 altogether. So our first point is going to be at 4, 5. Does that make sense to folks so far? Awesome. Let's plot these as we go, maybe. So I'm at 3, 4, 5. So go over 4, up 5, and that's our first point on the graph right here. I'm going to put in 2 more points, just like we did for the original toolkit function, root x. So I need a next best value. Good call. 5 would be a great one, because if you plugged a 5 here, this turns into the root of 5 minus 4. It's just the square root of 1. Square root of 1 is still 1, so this whole thing just turns into 1 plus 5 for a value of 6. Just like what happened in the green curve, right? The first point is at 0, 0. If you move right 1, you move up 1 to get the next point. Over here, move right 1 so that we're at 5. Move up 1 so we're at height 6. And there's our second point there. Now, anyone see what the next easiest, most convenient point would be for x? 8 would be a great call. If we plugged 8 there, we'll have the square root of 4, which is easy to work with. So we're in business with an 8. So 8 will give us root 8 minus 4 plus 5, which becomes root 4 plus 5, which becomes, this is just a 2 plus 5 for a value of 7. But just like here, when you move off 4 units to the right, we go up 2. Same with what's going to happen here. Our coordinates go 8, 7. So here's 5, 6, 7, 8. Here we're at a height of 6, so we just need to go 1 more. Here's 7. And if I could get that in just right, that looks about right to my eye. Here's finally the sketch of this curve. Now it was freehand, so it might look a little bit wonky. I didn't have perfect graphing paper, but the curve in green, we could just take this whole curve, move it over like that, and that's exactly what the transformation of functions is really doing. So Control Z works, there we go. All it did was move the green curve right 4, up 5. And that's the major idea of transformations of functions. That's the kind of things we'll be doing with this section here. Any questions at all, folks, on getting through this one? Okay, so like we said, all we had to use is just a couple things from this list, what's highlighted in yellow. I'll leave these down below after we complete a problem, just as a paper trail of what the formula was and how we used it. That's just not going to fit there, but we can leave it right there. Well, let's try this again, folks. I have 2 more functions, h of x equals x squared, and q of x rather equals h of x plus 2 minus 3. This one's a little bit different because here, g of x, they just gave us the function in terms of a square root. So on the new problem, we have a h of x, and the new function is defined in terms of h again, making it kind of a weird problem, but we can still get through it. Any questions before we start this one off? Okay, so same kind of strategy as before. I'm going to plot the original toolkit function x squared in green, the new function q of x. I'm not sure why q, but there it is. That'll be in blue. Here's our axis to start off. And let me add that statement we said before. I think these instructions would have read better, especially been more consistent with the exam if I said plot on the same set of axes. So that's something I would probably say on the exam if I intended to, and you'll have graphing paper right here, so your plot is not as rough as mine might be. Well, let's give this a try. First thing we do is just go to h of x and plot that function. If you plot it from memory, I'd say that's great, but this is always the go-to method if you're not sure. Plug in the x, and this time I'm going to use the y equals x squared. If we use a y equals something, keep in mind that y is h of x. So those two are going to be used interchangeably. Just a little bit faster to put down here. If you're dealing with the squaring function, well, a nice value might be, say, 0, right? There's no harm there. A next nice value might be +1, and then +2. Those would do the job. We plotted a parabola like this one the earlier week, but this one is just a nice one with no transformations that we did earlier. Plug 0 into y squared, we'll get 0. Then 1 squared is 1, and 2 squared will be 4. So we have a table of points. Now we're ready to go. Any questions at all so far, folks? Okay, plugging these in, first point is at 0, 0. Next point is at 1, 1. And finally, the next point is going to be at 2, 4. So we have our curve that goes up like this. But I plotted this kind of in an unusual way. In a certain sense, the way I plotted this one is not too different from the way I plotted this one. Notice, in fact, it's almost like the same curve, except the X and the Y coordinates have been flipped. Here, I knew I was done plotting because the domain of that goes from bracket 0 off to positive infinity. So that's where the curve should lie. But this one's different. Anyone recall what the domain of X squared should be? Exactly. This one's all real numbers. There's no restrictions on X squared. You could have put negative numbers in there with no problem. And that's an important thing to know, since if I stopped right here, like with the square root function, I only have half the curve. That's really kind of the value in these kinds of pictures. It might be a nice thing to print out to just have available while you're doing problems in ALEKS. Because if you know it was X squared, and we only plotted this much, well, we'll just reflect across the Y-axis and get all of the rest of the points in that way. So back down to our problem. I am satisfied with these points only because of symmetry about Y-axis. We go left 1, we have a point right here, left 2, we have a point up here at the same height. And so the rest of the curve, oh geez, I missed one, goes about like that. Just blow up that point. So there's our original function. Again, the value here is you don't have to memorize the graphics at the very top. This kind of work can help you produce it, but we still have to know basic information like domain of that was all real numbers. Well, we're off to the one in blue. And when we look at the one in blue, first let's do, again, our little analysis. We want to look before we leap. If that says -3, then that's the one that's normal. We just go down 3. And if this says +2, that's the weird one. Any volunteers for which way we should go on that? Exactly. Let's go left 2 units. So those are the major ideas to get through these. And the transformation we used is, let's see, these kind of ideas right here. I'll just paste it below as a really fast reference. If I can find a spot to zoom, there we go. So now let's go and sketch this thing. Now we use a table of values on the last one, but if you have a function given in this kind of format, don't want to zoom out too much. Sorry, just trying to make sure I can fit everything for us to see. There we go. I think that fits. If we have a function in this format, where Q is in terms of H, I think it's honestly just a little bit easier to in fact use this information, left 2, down 3. So let's try this new strategy for getting through this problem that's better suited for the format of the function. Now, here it's telling us the transformation we're using, what the function might look like, and what happens to your points. So let's analyze this by really just analyzing what happens to all these different points we have. We can start on, say, this point right here. This is the point 2, 4. So now when we say we're going left 2, down 3, let's do a little work over here. 2, 4. First, if we go left 2, what's going to happen on this is the first coordinate is going to go to a 0. So that's our shift left 2 units. The C there is the 2 that we have. So this will become a 0, 4. So that takes care of the left 2 transformation. Then this says go down 3. We're on that transformation here, row 2. Let me highlight these. And all that's going to happen to your point is you subtract the value. So if it says minus C, we'll do a -3 on that second coordinate right here. So this will turn into, let me try again. That was a highlighter. 0, 1. So that's really the action on the point this time of going left 2, down 3. We just subtracted 2 from the first coordinate, subtracted 3 from the second coordinate. And our new point at 0, 1 will go right here. So that's our point coming from 2, 4. Let's now do the point right here, say, or right here. That's the point 1, 1 next. First, any questions at all on how we transformed that first point? Okay, let's try it again. The next point I'm going to move is 1, 1. So what happens to 1, 1? You could do both operations if you like, but I'll just go in stages. We'll go left 2, so it'll be -1. Next transformation, down 3, but that's affecting the y coordinate. So subtract 3 from that positive one, and we get a -1, -2. So that's our second point. Let's go and plot that down. -1, -2 would go right here. And we're just about done. One more point. This one is 0, 0. So just like before, let's use the same strategy. 0, 0. We took one step on that. Anyone see what the resulting point would be? Exactly. The -2 comes from left 2. Means subtract 2 from the first coordinate. So -2, as you said. And if it says down 3, subtract 3 from the second coordinate. So this becomes -3. Now let's go back to the graph. -2, -3 would be right over here. So if I were to sketch this, it would go about like that. Then we use symmetry just like we did before. On the green curve, we only plotted half of it, then we reflected. Here, that's half of it. We can go right here. Left 1 to get a point at the same height as this one. Over here, we'll have a point at the same height at that location. And this finally completes our graph. So our original curve was h of x equals x squared, our basic function. Here we said we're going to take it, move it left 2, down 5. And there it is. It ends up left 2, down 5. This time the strategy was we just operate on the points using this table down here. Let me highlight the ones that we actually used. Well, we've done it, folks. That's pretty much how these kind of problems are going to go. We're just going to try to look at different kinds of transformations, different kinds of settings to get a feel for each one of these. Not all of them are going to be graphical like we see here. Some of them might be more algebraic, where we'll define a function, say what the function should look like based off the transformations. Well, any questions at all getting through this first one? Okay, let's now try. Move that down, there it goes. These functions here, and then we'll start switching gears a little bit so that all day today won't be just plotting. That'd be kind of brutal, I think. Here we have y equals absolute value x, so a nice absolute value function. That's another one of our toolkit functions. And here we have just a weird transformation. There's a multiplication on it, and that multiplication also involves a negative sign. So although it doesn't look like it, there's really two transformations altogether right on this one. But let's give this a try. First thing we want to do is take a big XY axis like before. Here's our absolute value function. We've worked with that function before, but you know what? I don't think we've ever plotted it. So this will be good practice for us. And here's -3 times it. So first, let's start off in green. We'll call this x. Y equals absolute value of x. And this one's pretty fast to get through. It's honestly feels like you're plotting a parabola, except there's no curvature. It's just two segments for this function that go off in different directions linearly. But we could put in 0. We take the absolute value of 0 to still get 0. We can plug in a 1. Absolute value of 1 is just 1. And if we wanted to, let's throw in a couple more points. We plug in -1. What would the output be right here then? Exactly, the absolute value function is just going to shear off the negative sign, converting everything to positive. If we put in, say, 2, we would get 2 back. Oops, didn't need to scroll. If we put in -2, still 2. Absolute value function doesn't care, just returns positive no matter what. So if we were to plot this, we have a point at 0, 0, much like a parabola, a point at 1, 1. And here's where it changes quite a bit. There's a point at 2, 2. And it just keeps on going off in that 45-degree angle forever, just like that. That's half the function. When we put in the negative values, much like the parabola y equals x squared, we have symmetry about the y-axis. What I mean by that is, if you imagine this is real paper and you folded it kind of like the arrow is indicated, this would overlap with the other part of the graph. So we can just immediately put a point here. Let's keep that in green, I think is a good idea. A point here. And here's what that y-axis reflection would look like. That finally builds the entire absolute value function, y equals absolute value x. Any questions about that so far? Okay, yeah, go ahead.
So when graphing, we always want there to be a mirror image of it on the other side.
Only if there is some kind of symmetry. Unfortunately, not all the functions have a symmetry.
Okay.
And that's kind of what happened on that one right here, the square root function. So again, this is a great set of functions to have just kind of available, ready to go, because just like you said, if you expect symmetry, plot one side and reflect over to get the other side. It'll work for this function, this function. This one's a different symmetry. This is about the origin. It's really two reflections. But the one with y-axis symmetry would be this, 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 and this all have it. Does that make sense with that question there? Awesome.
With example 2, that was one of the ones that would have symmetry, so you want to plot. So like, let's say we have that on a test, we want both sides to be graphed to where it looks symmetrical on both sides like this.
I see what you're saying. Yeah, you'd want to start like say at the local absolute minimum rather. Get some points going there and then just reflect over.
And that's with following those rules. So how do we know which rules to use based on what graph and coordinates and stuff that we have?
What do you mean by which rules
Like
we use?
the 1 through 4 that you copied.
Oh, gotcha. So what I did with the 1 through 4 is I first looked at a number that was next to x, and that's what's happening right here. There's a number next to your x. So it tells us we had to go left by that amount. Then when I saw the number away from x, the -3 right here, I was looking at this portion right here, which tells us shift down by that amount. Does that help with seeing how we picked those out?
And that's what you need to do to get the other side to be symmetrical, basically, just follow.
Oh, these rules right here was just to plot this curve right here.
Okay.
And then after that, we plotted just these points right here that gave us symmetry. We redid them over here as well. So we got that segment and then reflected it across. Awesome. Other questions so far, folks? Okay. Oh, well, you're asking about a different kind of reflection?
No, I was just wondering, if we had something that looked like it could be symmetrical, is that how you want it, is to have it graphed on both sides to where it makes that parabola shape?
Yeah, if we have symmetry, we have to have both sides of the symmetry. Other questions so far? Okay, well, let's try out this little thing again. We have the absolute value function that's plotted in. And by the way, just for a connecting thought, that absolute value function is a piecewise function. It's in the reading, but just to emphasize that, absolute value of x is really defined this way. It's x. If x is greater than or equal to 0, that makes sense. Absolute value is always giving you a positive. So if x is positive, give x back. And if x is less than 0, meaning it's negative, you have to go negative x. That way, if you put in, say, a -2, that would go inside here. It would be negative of -2, forcing it to positive. And the reason to mention all that is, if you look at this segment, I'm going to delete this in a moment, but just to connect the thought, this curve is y equals x, coming from right here. But we don't plot the whole thing. It stops right at this boundary point here. Then this portion, negative x, that's this curve going this way. That is y equals negative x. But again, it just stops right here because it only is valid for negative x's. So we just took two linear functions, y equals x, y equals negative x, jammed them together, and that's the absolute value function. Really kind of weird, right? I think it's easier to explain that function by saying it just returns positive no matter what. but this is what it actually looks like graphically. Well, I think we're ready now to go to the function in blue, but first, any last questions at the moment? Okay, let's give it a try then. So this function is definitely different from what we've seen before. We did make a note before that if you see a negative sign, anyone recall what that ought to do? It's going to reflect it, absolutely. And some people are indicating this way. It's reflecting across the x-axis. So the whole graph is going to kind of go like that, flip on its side. That's not accounting for the 3, just the negative sign. So let's put that as a note. This negative sign right here is a x-axis reflection. If you do an x-axis reflection, all that happens is you take all of your second coordinates, you multiply them by -1. That's what causes the reflection. Let's hunt that out in our list of formulas down here. We said reflection across the x-axis. That's the wrong one. That's property number 5. And essentially, this is the thing to look for. If you have a negative sign in that kind of way, you're just multiplying all your second coordinates by -1. Does that make sense to folks so far? Okay, then we have something new as well. This 3 that's right here is going to cause either a compression or a stretch. Now, I think that one is actually really kind of tricky to work out, whether it's a compression or a stretch. Where it comes from is on these right here. If you have a constant next to f of x, not next to x, but next to the function, think of the f here like the absolute value function, for example, then you're going to have a vertical scale change, compress or stretch, depending on the magnitude of your constant c. If it's next to x, well, it's a different kind of compression. It will compress horizontally. But certain functions, especially if you have already some symmetry, one kind of compression going this way is the same as another compression or stretching going this way. So these start to get really, really convoluted altogether. I would say these two, 7 and 8, are the trickiest of the entire list right here. Let's plug them in. I want to come back to them because they are important. But in all honesty, if your whole goal is to just sketch this, it might be better to just go to table of points and do that. Just write out where their points are and sketch those points. So we'll give that a try. If folks are curious, we'll show which one of these really came into play. So let's start off by going this way. We'll have a set of x coordinates. The y coordinates will be equal to -3, absolute value of x. We need to pick some nice points, but absolute value function is not so bad. We can do the same kind of thing. Pick a 0 for x, a 1 for x, a 2, maybe throw in some negatives, -1, -2, and now we're just going to start throwing them inside here. Starting with 0, you'll have -3 times the absolute value of 0. But by the way, when you write that, try to make it like it doesn't look like 101. You want to make the bars either bolder or just taller. But absolute value of 0 is still 0, and 3 times 0 is still 0. So we have our first point right here, 0, 0. Plug in a 1 right into this, you'll have -3, absolute value 1. But that just comes out as a -3. So when we plug in 1, we're going down 3 to this location here. Finally, if you plug in a 2, anyone see what the value should be for this one? Exactly. Absolute value of 2 is just 2 by -3. Gives us -6. So let's see, 3, 4, 5, 6. And that's our value right there. So we have a line coming out this way. And now we really don't have to plug these values in. We're expecting symmetry. But let's do it just for the sake of practice. Throw a -1 here. Absolute value of -1 is +1. So this turns into a -3. Likewise, if you take -2, throw it inside there. Absolute value -2 gives you +2 times -3. So that's -6. And notice they just duplicate again, and that's symmetry working for us. So let's plug those last 2 points. At -1, we're down to -3, so it's right here. And at -2, we're down to -6. So completing that sketch, that's what the second portion would look like. That's our absolute value function here. Well, we did it, folks. We have a nice sketch altogether. And now I have a question for everyone. We knew that we had an x-axis reflection just because of the negative sign. The curve in green just flips down and goes under. But 3 also changes the scale. This one's like steeper, right? And to your eye, what does it look like? Compression this way? Or does it look like maybe a stretching this way or a compression? So I'm going this way. Awesome. It absolutely is that. But again, because this function has a lot of symmetries going about it, you could also view it as, let's see, compression this way. That definitely makes the most sense to me. If we stretch it out going this way, I believe we would have really the same kind of effect for this kind of problem, which is really kind of weird. Let's go to where the notes are on this and see if we can track it through. I would want to say, though, that what we're about to do here, it might be considered optional, since this is really more tricky than it really needs to be if our whole goal is to just plot the function. So let me carry down y equals -3 absolute value x. Everything here is talking about a constant. So we have a constant, say 1/c, that obeys that information. We're looking at just the constant 3 there. There's also the negative sign handling the reflection, but that was property 5. We're deciding which one of these is really going to fall out. Well, we would have to write in a form of 1 over the constant. So coming down over here, this will be -1 over 1/3 times the absolute value of x. So now that we have it written in this way, we want to get the reciprocal in. So we have a constant in the denominator here. This 1/3 falls into this range. We can think of it as a vertical stretch if we really wanted to, and it's still the right picture. Although you're also right, you could think of it as a compression horizontally because of the symmetry in this function. But officially, for using these properties here, this is what it could really be thought of as, at least by this formula here. So the functions are wild depending on the way you view them. But our goal is just to get a good quick sketch like this. So I'd say you don't have to worry too much about those technical matters for the purposes of this class. If you can get through a table of points and you know you're expecting reflections and those kinds of things, then you're in really great shape. But other questions at the moment, folks, with this one here? Okay, well, let's try some other weird issues here. These are the major graphic ones that we were taking a look at. And now for example 4, here's where the work kind of changes gears just a little bit. When you see these in the homework, it probably doesn't feel great at first when you see this kind of problem, but it's actually a freebie. This one is a little bit easier to get through than kind of all the others are. It says we have some function f defined in this way, 5x² minus 3. And now it says if the graph of f is translated vertically upwards by 7 units and horizontally to the right by 3 units, it becomes the graph of a new function g. We just want a formula for that. And so we can start immediately by writing g of x equals. Now, going back to the function here, we have to first decide if we're going upward 7 units or horizontally right by 3 units, which one of these transformations, the green or the blue, is going to be affected right around x, where x is. Anyone happen to know? Sorry, say again. For the which one? The one in blue or the one in green? Horizontally to the right? Well, it turns out this one is going to be right around the x right here. The one that is going to be either up or down, it's the one that's going to go by the 3. So what we're going to take is, for this, we're back to just shifting things around. So we need this part of the table. Need to get a little bit faster at doing this. There we go. So let's start by saying, let's see, it's going to go horizontally to the right by 3 units. that means we're shifting right by 3 units. We're really on transformation property 3 on this. And so that means we're going to be putting something around X on this particular problem. So going back here, here's what it looks like to start. We put in a 5 where X squared is. First start with putting in a parenthesis. So here's where X was. It's now power 3. Then write in the rest of the function with a -3. This is the kind of stuff we would do if we're saying doing a composition, for example. We can plug in the X right here. And as it stands, that is the original function. But the moment they said go horizontally right by 3 units, we're putting something right here next to X. Now it's still tricky. Is this a +3 or a -3? Good call. It's always the opposite. I really hate that, but it's just the way the operations work. It's got to be a -3. And that's why we're seeing the minus sign right here on that property as well. So that's all right, set to go. Now we have to deal with this portion in green. In green, it says we're going vertically upwards. So shift up C units. We're in transformation number 1. And that's essentially all that's going to happen. We just tack on that amount to the far right. So up and down, think of that as things go the direction you would expect them. So +7 here. But if you're going left or the right in the formula, the number comes in backwards of our expectations. But this is essentially all we had to do. I mean, we still have to simplify everything. So g of x equals 5, x minus 3 squared plus 4. Then that finishes off that entire problem right there. Any questions at all, folks? Yeah, go ahead. You're saying you could also write g of x equals f of. Yeah, absolutely. Sometimes the instructions could indicate that we want to write out this way. It's going to kind of depend on the problem. So if it says find the expression for g of x, usually this is what they mean right here. Just write it out without using the function f. But here's what the instructions would look like for an answer like this one right here. I'm glad you mentioned that. The instructions would say, find an expression for g of x in terms of f of x. So if you ever see this kind of wording in terms of f of x, then this is the type of answer they expect right here. Honestly, though, if this was an exam problem or a quiz problem, if you gave me this, that's kind of what I'm expecting, I'd be happy. But if you gave me this one in yellow, that's a creative answer. It's absolutely correct. I would give full credit to that in a quiz or exam setting. Alex, though, they're expecting one kind of an answer or another. And so it kind of just depends on their wording. But other questions or comments with that so far? Awesome. Yeah, that's a great way to view these functions. That's kind of the theme of our notes so far. Sometimes, like on example 3, we just know what the function is. They just tell it to us. But other times, like in example 2, one function is defined in terms of another function, h of x, like you were mentioning here on that other problem. And so it's important to know how to get through these in either way, since they're both pretty common. Maybe zoom back to here. So again, this one's kind of nice because it's just an algebraic type of problem. There's no graphs. We still want to think about what would happen to the graphs. But that's the end answer, or this answer with those extra instructions. Any questions at all, folks, on getting through these? Okay, so that's working with transformations of functions. And to me, for all those kinds of problems, do you ever see something like this in Alex? I think these are the hard ones. We have a function that's defined as a piecewise function, one linear segment going here, another linear segment going there. For me, if I were to bring this problem in as an exam problem, I would probably put a solid dot here, here, and here, just to emphasize that's where the domain begins right here, that's the minimum value, the absolute minimum, and that's where the domain ends right at 4. Also, it's just something we're more used to seeing for these kinds of graphs. So here, that's the graph of y equals f of x. I'll just put a quick note here. And we want to draw the graph of y equals f of negative x minus 1. So this y function is defined in terms of the original f of x function. And now let's do the look before we leap portion on this. I like the negative 1. Is that going to go up, down, left, or right? Exactly. That one's a down 1 because the negative is after the x, it's not affecting it directly. So all points go down 1. Now the negative sign right by that x, that's new for us today. It's still a reflection. If the negative was out here where the red dot is, in front of the function, that would be a reflection across the entire, well, yes, x-axis going this way. But if the negative sign is here, we're going to reflect across the y-axis going this way instead. So let's take a look at those transformations. First one we're using is, we're going to go down 1. That's property number 2, which really isn't too bad. Next one we'll use is, you have a negative sign right there. That causes a reflection in the y-axis, which means if you want to reflect the y-axis, take every point, multiply first coordinate by negative 1, and that's all you really have to do. So we'll use both of these in order. We put this down below. Okay, so that's our setup so far. And now, because this is a function y defined in terms of some other function f, tracking what happens to all the points is, again, a really, really good strategy. So let's give this a try here. When you do this one in ALEKS, this one is very tricky because we're doing a lot of operations on a lot of different points. Everything has to go in exactly. It'd be really hard to do it in ALEKS without doing any scratch work first. So on your scratch paper, start by just indicating these points. This is negative 2, 4. Oops. There's a little button on my digital pen that I have to always remember not to press or weird things happen. Our next point is at coordinate 0, 0. And our final coordinate is at 4, 2. So we have 2 transformations that we're going to do. First one is we're going to shift down by 1. And the next one that I forgot to put a note in is that's going to be a y-axis reflection. Only because of the negative right here. So define what happens to the points. I'm going to go in order here. First, I'll do the shift, then I'll do the reflection. So for shifting down by 1, we just subtract 1 from the first coordinate. That'll be a 3. So we get to negative 2, 3. Then on the next transformation, we now need to do the reflection in the y-axis. But that just says, take your point, whatever it is, negate the first coordinate. So here's where the action is. Take a negative times that first coordinate. Let me also remind myself to highlight that portion there. So here, this is going to turn into a positive 2, 3. And that's our first point on the graph of that new function right up here. Does that make sense to folks on how we're operating on just the coordinates? Awesome. If we're happy with that, here's what happened. Negative 2, 4. We're reflecting across the y-axis, so it should end up right here. But then we're going down 1. That's where it should end up. If you're good tracking what happens to the points just by moving your finger across the grid, no harm done. But for me, that is very, very tricky, especially when you're learning these. So always it's a good idea to just say, go through the points, see where they end up. And 2, 3 is that first point. Does that look right to folks on that first one? Okay, let's try it again. We're on point number 2. This one is at the origin, 0, 0. So first thing we're going to do is go down 1. So this will turn into 0. And the negative 1 there is the down 1 portion. Now, this gets a little bit weird. If we reflect that point across the y-axis, we have to multiply the first coordinate, which is 0, by negative 1. But what's negative 1 times 0? Still 0, right? So the origin is kind of weird. It doesn't change. it's still 0, -1. But I mean, it shouldn't change. All that's going to happen is we're going down 1, so we're here. If we're on the y-axis and we reflect, all the points on the y-axis stay exactly where they are. So that's why the origin really doesn't move in the actual horizontal direction. It's just going to go right here. So 2 points down, we'll eventually connect the dots when we have the full grid. Last one is 4, 2. So let's go in order. If we go down 1, that 2 becomes a 1. So we're at 4, 1. Next, we're going to do a reflection. And anyone see what the final point should be after that reflection? Exactly. The first coordinate gets multiplied by -1. That's what this is saying down here. So -4, comma 1. So let's go in order. So this point, first, we made it go down 1. So it's here. We reflect across the y-axis. It should end up way over here. -4, 1. Now that we have all 3 dots, here's what the connected curve will look like. And it's kind of tough to see if it looks just right because a couple things happened to it. But it does look like it reflected, and then it did go down by 1. Just a lot for me to kind of visualize that all happening as, say, like a computer graphic or something. But going through the points is slow, methodical. It's a great way to do it. If you feel like you're really fluent with this and you can just put the points down, again, you're welcome to try that, but proceed with caution. It is kind of tricky. Any last questions, folks, on getting through this one here? Yeah.
So with, like, let's just use the last one as an example before we do. So you get the 4, 1 because you go down 1 from the positive 1 on the y-axis. Keep the x the same, and then to get the -4, 1, you just plug it into the formula that's highlighted in green.
Exactly, yeah. That's what we did, yeah. Exactly. So we first, right here in blue is the -1, so that's why we have a 1 there. Then here, that's the -1 times 4, getting that point, exactly. Other questions from our folks? Okay, well, let's see where we're getting into next. These are the major things we're looking at for transformations of functions. Let's see how we are on time. I did want to take extra time getting through this section because it's tricky. And so I'm going to leave this portion of the class all up to you. We can proceed through the notes, look at even and odd functions, or we can go to ALEKS and see what does an ALEKS problem look like in this kind of type of topics. Any volunteers for one way or another?
For the ALEKS.
All right, let's check this out in ALEKS. I think that would be a good way to end class today. Let's see if we can find stuff that looks just nasty. I think that's a good strategy as well. I forget they have a timeout on this. So what I'm doing is I'm going to the actual topic list. It'll take me just a moment. Kind of fancy in a way. This is what the math department set up for us. We are in section 3.5 as a part A, a part B. Now let's take a look here. Translating graph of a function, 2 steps. That already sounds pretty good. So this is about what some of these questions are going to look like directly in ALEKS. It says below is the graph of y equals 3x cubed. So that's the toolkit function, but because of the 3, it's also been stretched. So we have a nice function here, and we want to translate it to make the graph of y equals 3x plus 1 cubed plus 3. Now they gave us a tool here. This is just translation. If I click on this, I can take the whole curve and just move it around. Something you can't really do on paper. So ALEKS always feels a little different. But let's first, again, look before we leave. We want to know what happens with the plus 3. Is that up or down? Good call. We're going to go up 3 on that one. Then we'll look at the plus 1. And which way is that one going? Exactly, left 1 here. So left 1. So this is essentially all we have to do to get through this problem. We grab the manipulator key. We're going to literally just drag it left one. Let me try again. There we go. Once it's yellow, here's my left one and up 1, 2, 3. So that should be my new transformation. It's not too bad. It's a lot harder on paper, right? Because we have to actually sketch everything. We have to sketch the new points. But now this one is not terrible to get through. Let's see how close we are. Let's see, we went left 1, up 3. It's always kind of embarrassing when I get these wrong, but that can happen sometimes. These are very subtle problems occasionally, but that's how this kind of problem will go. Any questions at all getting through this one? Okay, what I'm trying to find here in ALEKS, I haven't gotten to this section just yet when I've gone through the homework. But what I look through is the ones that look like they're going to give us the most trouble. Like the ALEKS tools might be just a little confusing. So let me see if I can find something even worse. Let's see here. This one says on average, it takes 11 minutes to get through. That sounds like a pretty good one. Let's take a look at how this one ought to go. Oh, geez. For me, these are the worst kind of ALEKS problems because if you have 2 graphs, it's kind of double jeopardy, right? You have to get them both perfect now. And so I wish they would stop doing that. I'll give feedback to the math department. But it's 2 tricky graphs like we did before. We have to transform both of them just so. Let me zoom in on this one right here so we can focus on it. And the first thing to observe on the new function we're going to calculate is we have a negative sign right here. That's a reflection, but about which axis, X or Y? Good call. This is an X-axis rotation, or excuse me, reflection. If it was instead next to X, it would have been a Y-axis reflection. So this is a reflect across the X-axis. Now we did have a table that tells us what happens to all the points when you do that. For reflecting across the X-axis, essentially all that happens is a point AB will transform into the point, let's see here, across X-axis, we need to make it A negative B. So every point we see on here, we're just going to reflect the second coordinate and keep the first coordinate exactly the same. Does that make sense so far? Okay, let's give it a try. So first point I have on here, this one is at coordinates -2, 5. So using this information, that negative there is going to give us a negative right where the 5 is. We're going to go down to -2, -5. Let's plot a point. -2, -5. So one down, and we'll just do it all again. Now let's find the next point. This one is at coordinates -6, -3. Go back to the pencil tool. Anyone see where this new coordinate will go from here? Exactly. We're just negating that second coordinate, forcing it positive. So -6, +3 gives us something right here. Now, last thing to do is we'll use a line segment to join the points. And I wish you could check them halfway. You have to complete both graphs to know, is this right or wrong? But recall, if you know what that transformation should do, we should just be able to look at the page and see if it visually even looks like it makes sense. An X-axis reflection means fold the paper and the black curve should line up with the green curve. Does that look about right to folks? Awesome. Yeah, to me visually, that looks very, very convincing. So let's see if we can try one more. How about we make this one the last one for the day? Does that sound all right to folks? Okay, we did one like this, but again, for me, these seem to be the trickiest ones to get through. First thing I'm going to do is put down the coordinates so we can maneuver through these. It's at -5, -4 for the first point. This point is at, let's see here, 4, -1. And the final point way out here is at, looks like 7, -4. Now, I like the transformations they're giving us. This is just a one-step transformation. Oh, sorry, did I miss one up? Oh, hate it when I do that. This is -4, -5. Thanks for spotting that, folks. That was not a test. That's a real mistake. So this should be -4, comma -5. Phew, without that, we're definitely not going to get the right points. So good catch. I think the one we did in our notes is harder because this one is also just a one step, right? This is going to be a reflection across the y-axis this time. Only because the negative is attached, joined to the x value there. And a negative, or excuse me, a y-axis reflection means any point AB transforms into, this time you multiply the first coordinate by -1, not the second coordinate. So that's going to be all of our results. Let's see if we can get these in. So I'll use the pencil tool. Starting on this one, we're reflecting across, let's see, y-axis. So this should become +4, -5. So we go right here. That look all right to start out? Awesome, let's try this again. 4, -1. This should turn into -4. We're multiplying the second coordinate here, -1. So we're way over here next. And then final point. 7, -4 becomes multiply first coordinate by -1. So -7, -4. We're going to be way over here, way down there. So there's my points. We have to use the segment tool twice. So I'll join from here to here. And from this point to this point. And again, there looks like there's symmetry just by looking at it visually, right? No one part seems kind of off. So it looks like we really did a y-axis reflection to get through this one. Well, this is the scariest step. Any questions at all before we check our answer? Okay, I always feel nervous about these, especially again, we had to do two things at once. So let's see how close we got. Especially if this was the last one to finish the topic, I would double check it really fast. Let's see where we end up. Whew. It's always embarrassing to get them wrong right before you end class. It's happened to me before, but we're lucky this time. Well, any last questions, folks, before we call it a night? Yeah, go ahead.
So when doing the reflection here, whatever you're changing it to is a -A, positive B, but the x coordinate is positive, or sorry, negative.
Yes, exactly. Yeah, we'll have to just double negate getting it to the right sign. Well, have a great weekend, folks. When we come back, we're still going to be in this section 3.5. We'll be looking at even functions, odd functions. And I'll try to bring some more problems from the ALEKS system that look like they're just nasty to work with.